Good morning. Welcome to Mass 802, Algebraic Topology. So last time we were talking about different ways of constructing new spaces from given spaces. We have looked at two different ways of constructing new spaces from given spaces. If I say space, I'm talking about topological spaces. So this is a general remark. Throughout the discussion, whenever we say space, we are referring to topological space. I think we have seen the notion of subspace. So if you have a topological space, you can look at a subset of a topological space and define a topology on the subset to make it a topological space. We have seen that one. And then that definition was presented. You can refer to our previous lecture for the detail. And then we also look at the notion of product space. So if you have a family of topological spaces, you can also define on the Cartesian product of the underlying sets of the topology, a topology. And this topology is called the product topology. The topology in which, given any subset of the Cartesian product, there will always exist a neighborhood for the individual component or point in the space, so that the Cartesian product of the neighborhoods will belong to the set. So we have seen that construction. Now the next is to look at the next one we are going to look at is disjoint union spaces. So disjoint union space. So that is given a family of topological spaces. So a family, say X alpha, where alpha is some set. Let me use A. So A is just some, I can use gamma as my index set. So if you have any family of topological spaces, then we understand that X alpha is a topological space, so there is an underlying topology which we have not written explicitly. Then on the union, disjoint union. That is alpha in gamma. You can always form a disjoint union, call it X, of any family. Even if the set are not disjoint, you can form a disjoint union and it should be the set of all X, comma, alpha, such that alpha is in gamma and X is from X alpha. You can always form a disjoint union like this. You know, like you are having a family of set. Like you have X1 consisting of, element, and then you also have X2. If your family consists of only two sets, then you can form the disjoint union of X1 and X2 to be the set of all ordered pairs X, 1, X or Y, what, 2, such that X is in X1 and Y is in X2. When you do this, you have, it's a disjoint union, because by the time you take the collection of all ordered pairs X, 1, this collection will be identical, equivalent to x1, and that collection will also be equivalent to x2. But you see this set x1 prime, if we may call it x1, such that x is in x1, this will always be disjoint from the other collection x2 prime, defined in a similar way. So you can always disjoint the sets and then take the union. So that is how we define disjoint union of a family. So on this disjoint union, we define a topology by, so the topology tau, by declaring elements, a subset of the topology. Do we have duster? Okay. So please get me some duster. So by declaring a subset of X. So X is our disjoint union. So if you take a subset here, you say it is in here. So a subset, maybe U, let me call it U of X to be in tau if and only if. So what will be the condition? What will be the condition now is to say that the intersection of U with X alpha is open if and only if for each alpha in the in gamma, that is my index set, the intersection that is, let me just write it, U intersection X alpha is open in X alpha. But something is fishy here because U is a subset of what? Of X. And X is this disjoint union. Members in X are ordered pairs like this, X comma alpha. So element in U are ordered pairs, while element in X alpha are just X, the point X. So how do you see the intersection? So the way we are thinking here is that, there is always a natural embedding of every X can be embedded in here. If you define this map, X alpha into X, this I, given by a point is mapped to X comma alpha. This is an embedding. So every one of X alpha is naturally embedded inside this disjoint union. So there is a copy inside, and it doesn't intersect the other copies. Are you following? Of the other X alphas. So we are thinking that we have already embedded. So if you embed, that is, so what this intersection is, the intersection under this mapping. So intersection of U with this image. But then you now think of the pre-image of the intersection inside X. Are you following? So you have to pass through this embedding and take the intersection, then whatever you get is still a subset here, but the inverse image will be a subset of X alpha. So it is the inverse image of such that we are thinking. So it should be a member of the topology of X alpha. Are you following? Then if it is open in X alpha, meaning it is in the underlying topology of X alpha, then you declare U to be open in X. And then so this define a disjoint union topology. and the space is called the disjoint union of, so then U tau is a topology on X, and the space, okay, do you have the duster? Okay, thank you. And the space, okay, sorry. X tau is called, so it's a topology called the disjoint unions topology, and then this space is called the disjoint union space. It's not difficult to, the concept is the intuition is clear. So because these spaces are, you just have the spaces and then you put them side by side. And if you take any family, any subset, you now see the intersection with the individual members of the family. If it is already open, then you now say you have a topology, and that is called disjoint union topology, disjoint union space. Do you have any problem with this concept? I don't. I think it's clear because we are going to use it most of the time. You know. Let's say we have this space, and it is x1 is the cycle, for example, and if you take x2 to be maybe a torus, T2. This is how we write torus. Or you can think of a sphere and a torus. I hope it's okay. So on the disjoint union, so it is now the sphere and the torus. So you think you of having a sphere, and then you have your torus. You have a torus. So you have the union now. So you have the two spaces side by side. If I take any subset of this, that is, you cut a portion of this space and you cut a portion of this space to constitute of your subset, then you now look at the intersection, that is that portion that was cut from the torus. If it is open and the portion cut from the sphere is also open, then the U is open. Are you following? In the disjoint union topology. And then the spaces together will form a new space, which is the disjoint union space. But you know, this space is almost all the time a disconnected space, because it is this space with that space with this space. If these spaces are not intersecting, they originally are not intersecting, the disjoint union space will still be disconnected. Are you following? So this is just it. So if you put a sphere and a torus side by side together, they form a space. I hope it's okay. So this is what we think of as the disjoint union space. That is the intuition. So with this, we can go ahead to talk about quotient topology. This is the fourth operation on topological space, or fourth method of constructing new spaces from the existing spaces. So if you have any problem with this, you can still ask. If no, then we can now talk about quotient space. Quotient space, also called identification space. All right. So I start with a definition. Just like you have quotient group, in group theory, you can have direct product of groups. You can multiply groups to get an. Then you can also divide groups, because if you have normal subgroup, G by N is a quotient. You can do the same with a topological space. You can take quotient of spaces, okay, to construct a new space out of the given one, okay. So, so I start with a definition. So if you have a topological space, X, comma, tau, be a space, topological space, Y a subset of X, not necessarily subspace, just a subset of X. So any subset, let me emphasize it, of X. And also let Q from X to Y. So you see Y is included in X. So this mapping, let it be any surjective map. Because if you have to do it, sending everything onto this, you know, it can be onto, but you can decide to send everything to a point. But since Y has less element than X, you can take an onto mapping. It already exists. So be an onto map or surjective map. So let me use the word surjective. Be a surjective map. Sorry. Surjective mapping from X onto Y. Then once you have such a surjective map, you can use it to define a topology on Y. Okay? Then with it, we define, you see, this is not like subspace topology. You have a subset and you have a mapping. For a subspace topology, you don't require any mapping. But if you have an onto map, you can always define a topology. So we define a topology I can call it tau Q. So even for the quotient, the disjoint union topology, I just say it is a topology. You can go ahead to prove that it is indeed a topology. That is, the three properties of a topology are satisfied. Even here, even though it is a definition, you can check. It's not difficult to check. It's almost trivially true. We are defining it on Y, thereby making Y a topological space, because once you define a topology on a set, the set together with the topology will be a Y. Okay? So by saying by a subset, so still we declare a subset U subset of Y to be in tau Q if and only if U inverse, so tau U, you have Q inverse of U. What is this? That is the inverse image, the pre-image is set of all those elements in X that are mapped into U by Q. So if and only if this is a member of the topology, of the original topology. So take any subset in Y. If this pre-image is already in the topology, then you declare that subset to be an open set in Y. So with this definition, tau Q will be what? A topology on Y. And it will, and then you now make Y a topological space in this way. So if you have any onto mapping, a mapping from a set uh, onto a subset, from a topological space onto a subset, that surjective mapping can always do the job of constructing a topology on the subset and thereby having a topological space. In fact, I can remark that this Y doesn't have to, in general, even if it's just a set, not necessarily subset of X. So long as this, because this definition is not actually depending on the fact that you have a subset. Even if you just have a topological space and you have a subset without any topology on it, with the help of an onto mapping from the topological space onto the set Y, this set Y may not have anything to do with X. You can always define this topology. I hope it's okay. You can always say that I will take a collection of subsets in Y such that whose pre-image in X are open, and then that collection will describe a topology on Y. So any set whatsoever, once there is an onto mapping from a topological space onto the set, it will make it. So actually this condition is not very necessary there in defining this concept. In fact, so this topology tau q is called the quotient topology. Induced by what? By the map Q. By the surjective mapping Q. That's the quotient topology induced by Q. Okay? And Y will be the topological space obtained by the quotient topology. Or it will be the quotient space. Well. Yes. Yes. Here it's just a single set. Single set? Where? Where? What is your question? Sorry.
Now, what I mean is I didn't see the sense of quotient. In group theory, we have our quotient group is a set of subsets, different classes.
Yeah.
Well, in this one, it's just a set. The underlying element is element, not set, unlike in group theory.
The underlying
element in group theory, the quotient group, are subsets, different classes. Well, here the elements are just
the element of the topological space.
Yes.
Yeah, that's correct. Okay. No, we will look at many examples. You will see that even there, the underlying element are still subsets. You know, but what if, there are cosets in the group theory?
Yes, sir.
Okay, but what if all these cosets are trivial?
Yes.
So there are still elements of the group.
Yes.
So in fact, what you do is when you take quotient, the only thing is that in group theory, because you are dealing with cosets, so it's a very nice partitioning in which you partition evenly. Yeah, so therefore, but once they belong to the same class, you squeeze them and regard them as one point. So they are point. But if they are singletons, then you have, for example, if you form quotient with the trivial subgroup, you still just get the group back. G by the trivial is still the group back. So the same thing. The thing is here, the quotient here, the division of the space may not be evenly. It may not be an even division. So maybe some class will contain more elements than some. So in fact, you will see it that some classes may contain, you only need to take an equivalence relation to do this thing here. You know, because the equivalence relation is the fact that things in the same class with the same image under this, because definitely you will have, if you can see, you are taking a subset of X. So thinking of X, the Y is smaller than X because you have an onto mapping at least smaller than X. And that is why we say it doesn't have to be inside it. Just being inside it is to have the notion that you always have a bijective map, a surjective map. Yeah, sorry. So this is actually the idea. But you know, it is, you will see that actually it's a partitioning of the sets. It's taking the quotient of the set to yield another space, of a space to give another space. But when you are doing it, some classes in the equivalence relation may be singletons and some are not singleton. The classes that are not singleton, you will just regard them as one point, and then where they are singleton, they will remain to be individual element of the space. So even here, that squeezing is done, but not vivid. But we will consider many examples in this lecture to see that actually you are having so many. It's almost the same concept. It's the same concept. Because these groups that you are talking about, if they are topological space originally, but with group structure like topological groups, okay? And then if you have this, this Y is the quotient group, G by N, and this is G, and then you know you have a natural homomorphism, that is, every element is mapped to its quotient, cosets. So, but then since they are originally already topological spaces, then you can do the quotient topology, and it's still the same thing, but more presented in a more general form. Mapping, that map, it has a name. The map Q is called the quotient map. That mapping defined in this way is called the quotient map. So in fact, any mapping between topological spaces, such that if you have this a topological space and that a topological space, and with this mapping, so that this topological space is having the quotient topology, then that mapping induced by Q, then that mapping is called the quotient map. Okay? Actually, this is not the quotient space, but let me define the quotient space, because what is commonly known as quotient space. But then you always have a quotient topology in this way. So like we said, if now you have tilde to be an equivalence relation, on X being a topological space, and let X by tilde, since you have an equivalence relation, then you can talk of the equivalent, the space of equivalent classes. So be the set P such that P is in X. That is the space of equivalent classes. Classes under tilde. Okay? You can also look at the map, because there is always the mapping from X to X by tilde. Which map is this? Is the natural projection, you call it called? Natural projection. It is given by, if you take a P, it maps to the class inside here. So every element is mapping to its equivalent class under tilde. Okay? So we have a set. This is not a topological space. We don't know it because we have not identified any topology. But this one is a topological space. So since we have an onto mapping, in fact, this is why I had to make the remark that that Y doesn't have to be from a subset of X. So look at it. You have this. This is a topological space, and this is a set. Is that okay? But then you have an onto mapping because this natural projection is onto always. So can't we use the quotient topology induced by phi to make this one into a topological space? You can do that. So that space will be called the quotient of X, induced by what? By the equivalence relation, generated by the equivalence. Well, induced by phi, but what induced the phi? Originally, it is the equivalence relation that gave rise to the phi. So you go back to the originality. So you can always do that. So how do you do the quotient? You always have to have an equivalence relation. And then you, with the help of the equivalence relation, you define and induce quotient topology induced by the natural projection, you know. So this is it. Okay? So then, for x by tilde, together with this one. What is this one? This is the quotient topology induced by pi. Are you following? By this mapping. Okay? So this is called the quotient space. You remember when I wanted to call Y quotient space, I said, okay, it's not the one that is usually called quotient space. Because if you have quotient, if you are thinking of quotient, you should have one thing, then you think of dividing it. Are you following? Yes. So it's all right. So that is it. So it's called the quotient space, or it has a second name in the theory. It is called identification space. You will see why identification space of X by the equivalence relation. It is actually the equivalence relation that generates this space. So you use that space, that equivalence relation to generate a space. Let me give you examples. So the first example, okay? So we have, you can take X to be I. You remember I? The closed bounded interval. And let X be equal to this space with what? This is a subset of the set of real numbers. The real numbers is always having the standard topology. So this one will be the subspace topology. Are you following? We have talked about it. So, and let tilde be the equivalence on X, the equivalence relation on X generated by 0 is related to 1. So what I mean by generated by 0 is related to 1, it means every point is related to itself, and 0 is related to 1, 1 is also related to 0. This will be an equivalence relation. So each element here is related to itself. 0 is related to and so on. So what will be this one? If you understand this, what will be this? The quotient space. The quotient now. What will be this one? That is the set of equivalent classes. Well, 0 and 1, they belong to the same equivalent class. 0 and 1 are in the same class. So this will be like this. The class of 0, and others will be
Singleton class.
singletons. So you will have X, singletons like this, such that, so maybe we write it like this. We say this one, union the singletons, such that X is in the open interval. So every member of the open interval will constitute of an equivalent class alone. So this space will identify these 2 points. That is why we say identification space. So the end points are now identified. They become 1. Are you following? It's like you have a line segment, 0 to 1, and then you identify the end points. They become 1. But every other point apart from the end point are now they remain the same. I hope it's okay. So it's like you are taking the interval 0, 1, 0 to 1, and then you identify the end point. So the space, this is your X, but then the quotient space generated by your relations is saying 0 and 1 are at the same point now, they belong to the same class. So this is 0, 1, this is 0 now is equal to 1, because they are in the same class, and then every other point is the same. So this space is what? This is your quotient space. It's actually isomorphic to the cycle. You can see that. Homeomorphic, sorry. It's homeomorphic to the cycle. Yeah, if you take a line thread, a segment of a thread, and then identify the ends, you form a cycle. That is what we do here. So it is now a cycle. I hope it's okay. So this is another way to construct a cycle by taking the quotient of the interval 0, 1, generated by this equivalence relation. If you change the choice of the relation, the space will change. I hope it's okay. Yeah. So if you decide to identify maybe half, you say 0 and half are in the same equivalent class, every other point will be remaining the same. You know the space you are creating, then it will be what? Yeah, where this is 0 equal to half. You attach 0 to the half, and then every other point is on its own. This is 1, and so on. So but this is not isomorphic, homeomorphic to the cycle. I hope it's okay. So this is another way to construct a cycle. Okay? Do you remember the other way? How do you think of a cycle before? As the boundary of a disk. A disk of 2 dimensions. I think in the last lecture I made some mistake by writing R, a cycle as a subset of R. No, it should be subset of R2, not subset of R. Okay? The cycle should exist in R2 and not in R, because it's one-dimensional, but it is existing in 2 dimensions and the higher order dimensions. I hope it's okay. So this is my first example of the quotient space. The second example. The second example is to take, you can take a disk. This is our notation for a disk. Yeah, it's supposed to be B2, but then this is the, normally for a disk you write D. You remember what it is? This one, inside included. Okay, that is a disk. And let delta be the relation, be the equivalence relation generated by these two, while x comma y is related to minus x, y, and yeah, so that is it. So actually, so well, this is my relation. So what I'm saying, generated by this, for all x comma y in the boundary of the disk. Point of the boundary should relate to their opposite. So what you need to think of is, maybe you can assign some coordinates like this, because this is unit disk. The center is the origin in R2. So if you take a point here, x comma y, minus x comma y will be here. So you identify these 2 points. Are you following? You identify the 2 points. Okay? So it's like you have, all right. So, and then this point will be identified with this point will identify with this point will be identified with this. I'm very sure it is clear. So it's like you have the disks, and then you are folding it to identify the point. So you divide it through the diagonal, and then you fold it like this. I hope it's okay to identify the end point. So when you do that, so that point inside the disk, only point of the boundary will be identified in this way. So every point here will be identified with its opposite, but then point inside the disk will relate to themselves trivially. So for all xy in the disk, well, in the interior of the disk, point of the interior relating only to themselves. I hope it's okay. So the equivalence relation generated by this, with this equivalence relation, this x, so what will be this one now? X by tilde. So if you do it, if you can visualize what goes on there, you see that when you fold a disk and identify the side by side point, the resulting space will be like a sphere, because inside is still hollow. I hope it's okay. So it will be homeomorphic to S2, a sphere. I hope it's okay. All right. So that's another way of constructing a sphere. You can take a disk and construct a sphere. Before, we saw a sphere as a subspace of what? Subspace of a ball, 3 ball. Is the boundary of a ball of dimension 3. I hope it's okay. And there, we are thinking of it as the boundary using what? Subspace topology. When you think of it as a topological space, the sphere. But here it is using the quotient topology generated by, induced by this equivalence relation. I hope it's okay. So this is a very practical way of constructing topological spaces from the existing spaces. In fact, most of these spaces we are talking about are already manifolds, because this is a manifold. The sphere, this space constructed, which is homeomorphic to the sphere, is also a manifold. But you see, here for the sphere, subspace topology. But here with this quotient space, we are thinking of the quotient topology induced by the equivalence relation, but then the spaces are homeomorphic. I will give you a third example of this. I will continue to give examples until it is clear. And they are not just examples, these are spaces we will continue to be referring to throughout the course. Okay? We'll be talking about these spaces. So sometimes you think of a sphere like this as a boundary of the ball of dimension 3. Sometimes you think of a sphere as the quotient space obtained from a ball of a lower dimension. Well, of the same dimension actually. You can see that this ball is of the same dimension as the sphere. But when you are thinking of the sphere as the boundary, the dimension is of the ball is one higher than the dimension of the sphere. So all these things should be clear. So number 3, you can take I. You remember this? What is this one? Did you remember this? It's actually I cross I. This space is like this. Okay? So, and you are thinking of, since this is the interval, so this is 0, 1, 4. You can think of coordinate. This is 0, 0. This is what? 1, 0. This is it now okay? I think it's okay. This is 0, 1, and this is 1, 1. Okay? Yeah, so this is your I2, but it is the inside included. This is isomorphic to that disk. Homeomorphic, sorry. I'm used to the word isomorphism so much. So, but I mean homeomorphic. We are dealing with, with topological spaces. So, same means homeomorphic. So, this is the same as the disk, homeomorphic to a disk. So, regard this and consider the filter to be the equivalence relation on X, that is the square, generated by what? So by this one single relation, 0, y is related to 1, y. So what I'm going to do is this point here, all these points, they are 0, y. And then I'm going to identify them with this point here. This point are what? 1, y, because y is changing on this axis here. So all these points I will identify with this, which means this point 0, 0 will be 1, 0, will be in the same equivalent class as this. And this point will be in the same equivalent class with this. Are you following? So this quotient space will now be, yeah, it is this one now. So it's like you have this, and then you identify the edges. So it will be a cylinder now. Okay? So this quotient space will be this one. It is the cylinder. But then you identify it like this. Okay? So you identify this edge with that edge. So I'm talking about the surface of this cylinder. The surface, not the solid cylinder, it's a hollow cylinder. This is what you have. So this point now is this point and this point, but merged together. So they are now one point. But every other point in the surface remain the same. And this point and this point are merged together in somewhere at the center here. And then this is 0, 0, and 1, 0 merged together over here. And then you have a resulting space. And this space is homeomorphic to what? To the sphere. Remember how we constructed a cylinder. This is cylinder. It is S1 cross 1. SI cross 1, the cylinder. S1 cross I. That is a cycle, the Cartesian product of the cycle. The product of cycle with the interval. Finite cylinder, yes. Yeah, I mean finite. It's okay. Infinite cylinder is when you take the Cartesian product of the product of the cycle with the set of real numbers. Then you have an infinite cylinder extending in both directions infinitely. Yeah, if you use R here. So you have a cylinder in this way. So a cylinder can also be thought of either as a product space, product of the cycle with the unit interval 0, 1, or as the quotient space of the square generated by this equivalence relation. You know, where the edges, one side, the sides here, the edges are identified. I hope it's okay. Once you identify these edges, you obtain a sphere. Then you have a sphere. This is a topological manifold space. Then you now identify this space. So this is in another way you can think of this. Practically, it's like you are gluing. You know, when you glue a space, you use gum to press distance, to glue distance together. It's not a topological property because this point and that point, they were not within the neighborhood. You know, they are not together before. And now you bring them close together. And this point and this point, they were not close together. But when you do the gluing, you merge points, and then points that are not nearby are now nearby. Are you following? So it's not a topological property. So this space you are obtaining is entirely a new space. It's not homeomorphic to the original space. This cylinder is not homeomorphic to that one, even though both of them are dimension 2 spaces. Okay, but what is the boundary of this space? The boundary of this space is a cycle. You remember that? Okay, the boundary is this square. You know, this is the square here is with the inside included, but here is just a cycle. This is homeomorphic to the cycle, but the boundary of this one is a copy of two cycles. This cycle at the top and this cycle at the top. And that is enough to see that they are not homeomorphic. I hope it's okay. So my third example, this is my third example. The fourth one is you still take that space. So I will continue to be taking this space because see the identification we have here. So if you take X to be the space I2, so still this space. So I'm going to be you see, this space is also called a strip because look at the way I draw this thing. You remember, it's okay if I draw this like this because I have, you remember, it's rubber. You can stretch it. If you stretch it, it will be elongated, and so it doesn't have to be. This is still the homeomorphic to that one. Okay, and if you fold it and attach it, the way we do it when we do the identification, we just folded it like this. So it's like this one, and then I folded it. We do the folding like this. We folded it like this, and then we and what we do was to attach it together. Okay, so if you attach it like this, this is still the same identification with this one. So this is called a strip. It's a strip. Okay, but if you instead of attaching it like this, I'm going to attach it in the opposite direction. Okay, so the tilde will be the equivalence relation generated by, so this time around, what I'm doing is to identify this with that.
Yes, sir.
So 0, 1 is 1, 1. Okay? And if you do that, you get so 0 y to be identified with 1, 1 minus y. Okay? I don't know whether that is clear. Okay? Huh? 1, 1 minus y. So that if y is 0, so you're identifying it with that. And if y is 1, then you're identifying this point with that point, and like that. So which means we are identifying it in opposite direction. This is going like this, and this is going like. So you do the attaching like this. So which means you have to turn it. Okay? You have to turn the edges before you can attach it. So it's like you have this one, and then you fold it to glue. But before you glue it, you want this edge to come to be glued with the other edge. So what you will do is to fold it. Okay, let me have a, no, we can still use this one. Let me cut this paper so that I can show you what I mean. So it's like you want to glue this together, but if it comes together, this is still the cylinder. This one will still be a cylinder, okay? But then before you attach it, you reverse the order so that this edge at the bottom will be attached to the edge at the top. So you have to turn it, give it like one twist or half a twist. You twist it. So it is going to be this object. So there is a twist before you attach it. This is not a cylinder. In fact, this object has only one boundary. The boundary, it doesn't have inside and outside. This is called Mobius band or Mobius strip. So that is what you will have. So, but is it possible to draw it? This is can we draw it? Let me see whether I can try. So, so at this level, I have to twist it before I attached, and then we attach it. Yeah. Yeah, because if it comes like this, you have to twist this one. So you do the twisting, and then you can now glue it together. Then once you do the gluing, you have what is called Mobius strip. And the Mobius strip is this one. So that is what we have. Okay. So we have sorry, I'm just trying to, yeah. So you can see we attach it at this point. So it doesn't look like it, but it's okay. Yeah. So things is a bit better, okay? So I mean the surface of this thing. Okay. That is what we call Mobius strip. Okay? And it doesn't have inside and outside, because if you start traveling like this on the boundary, you go like this, then you can now come, and here you are at the other side. Okay? So it has only one side. Okay? So if you are to move around along the edge, you see that by the time you come back to the starting point, you must have traveled all along the edges. So actually the boundary is just a cycle. So the boundary of this thing I don't know that I can draw it again. So, but it is, yeah, I think I can draw it one more time. Yes. Yeah, I think it's okay. Go. So what is the boundary now? The boundary of distance will be a cycle. It's actually a cycle. It's a cycle. Even though it will not look like it is, the boundary is an entangled cycle like this, like a knot. You see, it's cycle but entangled. But you can, it is still homeomorphic to a cycle. It's still homeomorphic to a cycle. I hope it's okay. So the boundary of this thing is a cycle. And so it is not homeomorphic to a cylinder. So when we change the choice of our equivalence relation, the quotient space changes. It's a different quotient space. It's not homeomorphic to the cylinder because the cylinder is you see this thing, it doesn't have it's a it doesn't have inside and outside. This object, it does not have inside and outside. It has only one face. But the cylinder has two faces. There is the inside of the cylinder, and the outside of the cylinder. I hope it's okay. All right. So it is called Mobius strip or Mobius band. This is called Mobius strip or band. It's a very nice object. Mathematicians or topologists are studying it. All right. Okay. So we can look at the fifth example. I think it's okay. We can still go through the remaining examples. Number 5 is when you still consider x to be I and filter the relation, equivalence relation, so equivalence relation generated by so well, this time around we are thinking of adding identifying both sides. So we are thinking of this so we have this object is our I square, and then we want to identify this with this and that with this. Maybe I don't have to write the relation is generated by 0 comma y is related to 1 comma y, that this and this go, and then x comma 0 related to x comma 1. Yeah, it's okay, go for all x and for all y, and then the interior points remain the same. I hope it's okay. So this x and y are at the boundary. Okay, so this boundary will be identified with this boundary and this boundary with that boundary. If you do the first identification, it's just a what? A cylinder. It's just a cylinder. If you identify for the first so it's just a cylinder, the first identification. And so you identify it like this. But then this one was to be identified, this side is to be identified with what? With this side, straight. So which means you You first form a cylinder, and then later on you identify the edges of the cylinder. Once you do it, you get the resulting space to be this one. So it's going to be it's going to be this one. Yeah, it will be this one. It's going to be a donut, a torus. This is the space. Surface of this thing. Okay? That will be the space. And this is homeomorphic, so this will be your x by tilde, and this is homeomorphic to T2. So this is another way of constructing T2 from where? Using an equivalence relation defined on the space to this particular equivalence relation to generate it. So this is a torus. It's still a torus. Okay? We have seen this one already. There is another way you can also, well, we have not exhausted all the possible ways, because what if I join it straight, but this one's in the opposite direction? You see, it will still give a different space. So we can try that one. So number 6, okay? So you still take x to be I2, which is this one. Maybe I don't have to now write, or you can still write it. So tilde to be generated by x. Well, first of all, y, 1y. You join straight, but the opposite side, you join in the opposite direction. So 0, x, comma 0 to be identified with 1 minus x, comma 1. Yeah, this will be the generators of your equivalence relation. If you do that, so you're identifying this with this and this in the opposite direction. When you do that, you see the first instance you do the sphere, the cylinder, but then you now turn the cylinder and identify it. But before you identify it, you have to turn it in the opposite direction. You see, this space is not possible to, you can't do that in our world, because the world is 3-dimensional. So if you must to do it, you have to go to 4D. That is a 4-dimensional Euclidean space. Only there you can be able to do it, because this is what you will do now. When you form the cylinder, this is the cylinder. Now, sorry, even though it's not going to be, it's a rough drawing, you have formed the cylinder, and then you want to now glue these ones in the opposite direction. So, you see that if you have to do it, this is the cylinder now. So you have the cylinder, and then you turn it around. Sorry, I don't know that I can draw this thing. You can. No, this is in this direction, Ko. So, and then you want to now attach it. It's not, well, it's going to be this one, because this is, the arrows are facing like this. When I turn it, it will be facing like this, okay? So, and you see, if you take it up and put it, you see that the arrows will be facing different direction. This arrows, if I do like this, so the arrows here will be facing this direction and this. So that's not the right way to do it, okay? But what you want to do is to, you want to twist it? You can't do that. If you want this to come together, this object must pass through itself somewhere. It must penetrate somewhere here. passing through itself. You see, but once you do that, that is a discontinuity in 3 dimension. So, but if you are in 4 dimension, it's possible. It can pass through itself in 4D. So at the end of the day, what you get is this. So you get this object. This is how they normally draw it. I think I can. So this is what you get at the end of the day. So that you bring them together like this and glue them. So it pass through here and then you glue them inside. You see. And then you have a new space. This is your x by tilde, the quotient space. But this quotient space is existing in 4D. It's 2-dimensional, but it is in 4D. And it's just like the Mobius strip. This one doesn't have inside and outside also. It doesn't have inside and outside. It has no boundary also. It's just like the donut has no boundary. The boundary of the donut is empty. And this one too has no boundary because you have glued all the boundaries together. It is called Klein bottle. It's a Klein bottle. You can never be able to fill it with water. You start pouring water inside. So there is no inside and outside. So you can continuously be putting the water. It gets filled up and then it start falling out. So this is Klein bottle. Okay. This is we have the last object. So maybe what I will tell you is that this Klein bottle is a union of. It can be seen as a union of two, maybe union, no, not union, not disjoint union, like a union of two, like you can, there is another way, I just want to give you another way of constructing. If you have 2 copies of this Mobius strip, you can take 2 copies of Mobius strip. I don't know, we don't have sellotape, we will have glue them together so that we have a Mobius strip and another Mobius strip. So if you take these 2 copies of a Mobius strip, see, remember I told you the boundary is a cycle, and the boundary again is a cycle. So you can glue them together along the boundary. These 2 Mobius strips, I can start gluing them together along the boundary. But you see, this exercise will not be possible in 3 dimension. Only in 4 dimension you can do it, because there are times that you have to allow one of the strips to pass through the other. But so since you don't have the other axis to exit and do the passing, that will not be possible here. So, but once you are able to do that, you come up with a new space by gluing the 2 spaces together, and that new space you come up with is still the Klein bottle. So this Klein bottle is just like gluing the Mobius strip along the boundaries. I hope it's okay. So you still get the Mobius strip in that way. The last one is will be number 7. Number 7 is so you can guess what the number 7 will be. Is still I2, but then this time around, but I'm going to generate using 0y, 1 minus y, and then x0, 1 minus x1. So this time around in the opposite direction, and here also in the opposite direction. So everything in the opposite direction. Nobody can do this thing. No, at least not here in 3 dimension, because we are talking about doing it first in the opposite direction. This one is doable. When we do it in the opposite direction now, it is going to be a Mobius strip. But then we now take the other sides, but they are now just one side. and also do in the opposite direction. It's going to be a whole mess. This is like twisting everything together. Eh? No, you can't draw it. Okay? But there is a way a mathematician think about this thing. Just like you can see this Klein bottle as a copy of a Mobius strip. It is a Mobius strip, and then you have Mobius strip, you glue it with another Mobius strip, two Mobius strip together. You take two Mobius strip and glue them together to get this Klein bottle. So you can do the same here. This time around, this object, the quotient space generated by this, induced by this topology, quotient topology generated by delta, is a space called is RP2. It is called the real projective plane. Real projective plane. Projective plane, but real projective plane. There is so many ways of thinking about this thing. But you can think of having a disk Mobius strip first. Maybe you have a Mobius strip. And you say cycle. The boundary of the Mobius strip is a cycle. Cool? Then if you have a disk, I don't know whether you can, a disk can be think of like a perforated sphere. So a disk, one-dimensional disk, actually a sphere and a disk are of the same dimension. So you can think of a sphere, sphere like this, but with a hole. So if you have a hole at the sphere, this is a sphere. This is homeomorphic to a disk. Yeah, because if I have a disk, I can just, if it is a rubber, I can make it. Reality is that you can't close. If you close the boundaries, it becomes a sphere. Okay? So this is still a disk. So what you will do here is to start stitching, this Mobius strip along this cycle. Because the boundary is a cycle, and this one is also a cycle. So you start attaching, gluing this along the boundary. Once you do it, it's not possible. You can't do it here, like I said, but mathematically it is doable. So once you do it, you obtain a space, and the space you obtain is this sphere with Mobius strip attached to the boundary. So you cannot draw that which is there, but you can just put some lines like this. So this resulting space is actually homeomorphic to this real projective plane. It's this real projective plane. So that is another way of thinking about this real projective plane. In fact, we will talk about it more in the subsequent discussion. So this is so what I have mentioned today is two things. That is disjoint union, and then we now talk about quotient spaces. And we have seen so many examples of topological spaces that are quotient spaces, and all of these ones are also manifolds. I hope it's okay. So in the next discussion, we are going to talk about two more operations on spaces. The first of which is adjunction spaces, which is a spatial kind of quotient space. You can take a space, for example, I can take a cylinder and take this space and then attach it to the cylinder. This is also called attaching spaces. So the base of the cylinder here, you glue on top of the disk or of this plane. Then you obtain a new space. So this is still another way of attaching. You can glue spaces together and still get, you see, all what we have been doing is only one space. Then you now identify its edges or some of the point and make them one. This is quotient, but then you can attach spaces. You can glue spaces together, just like what I was thinking here. So you glue along the boundary. You can think of projective space like this, or this one you glue two Mobius strips together. And then the other operation is connected sum. We are going to talk about it in the next class, connected sums. You know, the process of doing connected sum is called surgery on topological spaces. So there's like, or surgery on manifolds. When you do that, you obtain a new space. I think we stop at this point. Thank you very much. I will see you in the next class.